In the last section of Chapter 5, we are going to talk about the binomial and geometric probability distributions. So the binomial distribution is when experiments or situations result in what are called dichotomous responses. So those are responses for which there exists two possible choices. So true, false, yes, no, defective, non-defective, male, female. It looks very differently depending on what the situation is. So simple example, tossing a coin where there are only two possibilities, heads or tails. There are many other types of experiments similar to a coin toss where you have a success or failure of a certain outcome. So they give us a probability distribution called a binomial distribution. So with binomial distributions or binomial experiments, they have to meet 4 conditions, and all 4 of these conditions must be met. Some of them are typically always met in a binomial distribution, and you look specifically for a couple of them. So one of them is that each observation falls into one of 2 categories, typically referred to as success or failure. So success really depends on what the experiment is looking at. So if you're looking at the number of people who get colds after being doused with water on a winter day, success would mean getting a cold, and failure would mean not getting a cold. There is a fixed number of n observations. So the first 2 are the big ones. Those are the ones that you're going to want to look at first before the last 2. So the n observations are independent, so knowing the result of one observation tells you nothing about the other observation. So usually that one is not no. It can be if you're looking at like the marble situation where you have 2 marbles in a bag and you're either pulling out a red or a blue, like that wouldn't be independent. Because each time you pull a marble, the probability of the next one changes. And then lastly, the probability of success, P, is the same for each observation. Now typically if 3 is no, 4 is also no. So 3 and 4 kind of go together. In terms of either meeting or not meeting the condition. Okay. So binomial distributions. So the distribution of the count x successes in the binomial experiment with parameters n and p. So the possible values of x are the integers from 0 to n, and we use the notation x is approximately b parentheses np. So n is the number of trials and P is the probability of success. Okay. So for our examples, we are going to determine if they are a binomial setting or not, and if they're not, we're going to explain why. So we go through the 4 statements above and check that they're all met. So first we have tossing 20 coins and counting the number of heads. So the first thing we want to look at is, are there 2 outcomes? Yes. Heads, no heads. 2, are there a fixed number of trials? Yes, we're doing 20, we're tossing the coin 20 times. 3, are the events independent? Yes, the probability of one coin coming up heads does not change the probability that the next one does. And lastly, is the probability of success the same for each observation? And that is also yes, because the probability each time is 0.5. So this is binomial. Okay. Example 2, picking 5 cards from a standard deck and counting the number of hearts. We replace the card each time and reshuffle. So the important thing here is that last sentence. So the first one is, are there 2 outcomes? In this case, yes. It's either a heart or it's not a heart. Secondly, fixed number of trials. Yes, 5. 3, are the observations independent? So here's where that last sentence comes in. So if we didn't know that we were replacing the card each time, it wouldn't be independent. But because we're replacing the card, it's independent. And then the probability of success is the same. And yes, there is a 25% chance that you select a heart. So this one is also binomial. Okay. Next, we have picking 5 cards from a standard deck and counting the number of hearts without reshuffling. So here is where we are not going to meet a binomial distribution. So it's not independent, and probability changes. So because we're not returning the card, the probability of selecting a heart changes based on whether or not the previous card was a heart, which then also changes the probability each time you draw a card. So this is not a binomial distribution. And lastly, choosing a card from a standard deck until you get a heart. So not only are the exact same 2 outcomes from the third example being violated, but also there's no fixed number of trials. So I didn't, like, if you're looking through the 4 steps, yes, step 1 is met. It's either heart or not. But then we go to step 2 where you're looking at a fixed number of trials. No. So this is not binomial. So we can see how wording through examples 2, 3, and 4 can change whether or not we have a binomial distribution or not. So next we're going to take a look at calculating binomial probabilities. So we have an example where Calvin is about to take a 5-question true-false quiz for which he is not prepared. He will be guessing on all 5 questions. So we want to know the probability he gets all of the answers correct, he gets them all wrong, he gets exactly 3 answers correct, and that he will pass the quiz. So we can do this without using the binomial distribution, okay? This is what we were doing with our probability distributions in the previous sections. You know, we can count the number of outcomes where he gets a question correct and do it that way. So let's use C to denote a correct answer and W denotes a wrong answer. And we're going to list all the possible combinations of correct and incorrect responses on this quiz and make a probability distribution. So X is the number of correct responses. So I'm going to make a pretty large table here because we are going to include all the outcomes. So X can equal 0, X can equal 1, X can equal 2, 3, 4, and 5. I wanted to leave some more room between some of the more likely outcomes. So he gets none of them correct. So that would be 5 wrong answers. Probability he gets 1 correct. So we can do correct, 4 wrong, wrong, correct, 3 wrong, 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 correct, wrong, wrong. Yeah, so 5 different ways depending on which question he gets correct. If we're looking at 2 correct, there's going to be a lot of outcomes here. So correct, correct, wrong, 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 correct, wrong, correct. Whew. Sorry, I almost added too many W's. there's 2 more. I'm trying to make sure I got them all. I'm missing one. Here we go. Wrong, wrong, correct, wrong, correct. Yeah. 3. It's the same as x equals 2 with W and C switched. So there's still 10 outcomes, but I'm not going to redo all of them. So 4 correct, there's not as many outcomes. So there's 5 outcomes, and then getting them all 5 correct, there's 5. All right, so when it comes to our probability, so we need to figure out how many total outcomes there are, and there's 5, 10, 10, nope, sorry, 1, 5, 10, 10, 5, 1. So that is 32 outcomes. So 1 out of 32, 5 out of 32, 10 out of 32, 10 out of 32, 5 out of 32, and 1 out of 32. Okay, so now we can go ahead and answer the question. So probability he gets all answers correct. So that is the probability that x equals 5, which is 1 out of 32. He gets all of the answers wrong, so that's the probability that x equals 0, which is also 1 out of 32. Probability he gets exactly 3 correct, so that's probability x equals 3, which is 10 out of 32, and then the probability he will pass. So on a 5-question quiz, 3 out of 5 or more is passing. So that's the probability x is greater than or equal to 3, which is the probability x equals 3 plus the probability x equals 4 plus the probability x equals 5. So 10 out of 32 plus 5 out of 32 plus 1 out of 32, which is 16 out of 32, which is half. So 50% chance that he passes, which you think would be different considering it's a 5-question test, but it ends up being 50%. So this is the long way and the hard way to do binomial distributions. There is an easier way, and that involves using our calculator that uses a formula to talk about. So it does not make sense to always create a probability distribution table for binomial distributions. It can take a very long amount of time. So there is a formula where the probability of x equaling any outcome k is called n choose k times p to the k times 1 minus p to the n minus k. So the notation that I used for n choose k is a little bit different than we used before, so I went ahead and wrote it underneath. It's just another way to write choose. So the n choose k is found using the formula from combinations, so n factorial over k factorial times n minus k factorial. So n and P are the same as they were before, but now we're adding in K, where K is our number of trials. Sorry, number of successes. So N is still our number of trials. But K is now our number of successes, and P is our probability of success. So there is a way to do this on your calculator. So just to refresh, in order to do a combination, so we do math over to PRB, and then we choose 3, which is NCR, but we're replacing R with K here. So that's the only shortcut. Everything else you're gonna have to plug in. So you're still have to use P to the K and 1 minus P to the N minus K, but you can use the NCR shortcut for that choose part. So let's just go over what each part of that formula represents. So the probability of X equals K. So this is the probability of K successes. And then we have N choose K. So this is the combination of K successes in N trials. So that part of the table where we did the 1, 5, 10, 10, 5, and 1, we did that by hand. This is how we do it using the calculator. Then times P to the K. So this is the probability of success raised to the sum of successes. So if you think, like if I'm looking at, all right, what's the probability, I do the 3, I would have to take the probability and I'd have to multiply it by itself 3 times. So that's why we raised it to the exponent. And then 1 minus P to the N minus K. So we also have to take into account the probability of failure. So probability of failure raised to the number of failures. So like if I got 3 questions correct, I would also have to take into account that I got 2 questions wrong. So this is a much shorter way of doing a binomial distribution instead of creating our probability distribution and then counting, because that's very time consuming. So if we're doing our binomial setting, so we have to make sure, so this is like a little acronym to help you to remember. We have to check that it's a binomial binary trial. So 2 outcomes. Independent, so the trials must be independent of each other. N, number of trials, and then S, same probability of success. So bins, if you want to like kind of help remember. So we're going to go back. We're going to use Calvin's true-false test. I've kind of already said it's binomial, but we're going to go back and we're going to make sure. So first, binary trial. Yes, you can either get it correct or wrong. Is it independent? Yes, each guess is independent of the next. Third, number of trials is fixed. Yes, N equals 5. It's a 5-question test. And lastly, same probability of success. In this case, yes, the probability is 0.5 because it's a true-false test. You have the 50-50 chance of getting a probability correct. So we're just going to redo 2 of the problems that we just did to kind of see how we get the same outcome in a much shorter time period. So let's do the problems. What is the probability Calvin gets exactly 3 correct, and what's the probability Calvin will pass? So probability exactly 3 correct. So that's probability x equals 3. So we're going to do n choose k. So n is 5, choose 3, times p, 0.5, raised to the k power 3. Probability of failure, 0.5, and then the remaining 2. So to get to the 5 choose 3, math over to PRB, and then 3. So 5 choose 3 times 0.5 to the 3rd times 0.5 squared. And we get 0.3125, which, if I were to convert to a fraction, is 5/16, which is the same thing as 10 over 32. What's the probability Calvin will pass? So that's the probability x is greater than or equal to 3. So there is a shorter way to do this. So typically we would do the probability x equals 3 plus the probability x equals 4 plus the probability x equals 5. But with binomial distributions, this can be very time consuming. So what we're going to use is the summation button on the calculator. So we call it sigma. So you go to math, and then you go to 0. So when it comes to plugging this into our calculator, okay, we do sigma. We're going to do x equals 3 at the bottom because we're starting at 3, and at the top is 5 because that's our last value. All right. And then we'll do n choose, typically it would be n choose r. So we're going to do 5 choose x because our value is going to, our r is going to change each time. So x equals 3. So 5 choose x times probability success 0.5. And then that's to the power of x. And then times the probability of failure, .5 to the 5 minus x. And then you hit enter, and it gave us 0.5, which is the same thing as 1/2, which is what we got when we're by hand. I understand doing the sigma notation is going to be the most difficult part, so I will definitely work with you to get down the sigma notation so that you understand it. Because we could do this by hand. We could do x equals 3, we could do x equals 4, we could do x equals 5, and we could add them up. But we're going to get questions where we need to do it for 7 or 8 numbers, in which case doing it by hand is way too time consuming. Okay. All right, so now we're going to talk about doing binomial distributions on the calculator. So there is, on the calculator, there's PDF and CDF, which is a difference. So PDF is a probability distribution, and it's used with the distribution when you're trying to calculate probability of x equals k. So if you go to second vars, and then the if you go all the way down to A and B. A is Binomial Pdf, and B is Binomial CDF. Okay, so we could have done the exact problem we just did by hand using Binomial Pdf. So let's do that with the probability that Calvin gets exactly 3 correct. So probability of x equals 3. So on some of your calculators, it's going to look a bit different. So it should be Binomial CDF, and then the first thing you need to put is n, your number of trials, then comma p, the probability of success, so 0.5 in this case, comma k, the number of successes, which is 3. And then you hit enter, and we got 0.3125. So even quicker than what we just did, but you have to know both ways because you will be asked to do it both ways. Okay. Then there's also cumulative distributions, and it's used when the distribution you're trying to locate has an interval of values. So specifically, probability of x less than or equal to k. So if we want the probability Calvin will pass, which is the probability that x is greater than or equal to 3, we would do 1 minus the probability x is less than or equal to 3, because they both have to add to 1. Sorry, less than or equal to 2, because we are equal to 3. So it's going to be 1 minus binomial CDF, and then 5.52. So 1 minus 5, 0.5, 2. And we get 0.5. So just to remember, binomial distributions, binomial random variables are discrete, so the inequalities do matter. So the calculator can only do less than or equal to. So if we're looking for strictly less than or strictly greater than, can't use the calculator. If we're looking for greater than or equal to, we have to do the 1 minus, and if we're looking for less than or equal to, we can just use the calculator. So let's do a couple more examples. So let's go ahead and use the calculator, the binomial PDF and CDF. So if I want the probability of x less than or equal to 1, we're going to do binomial CDF. So we are given that, so if we look at our example, it says the number of outcomes is 5 and the probability of success is 0.4. So 5, 0.4, less than or equal to 1, we put 1 there. And we get 0.33696. Okay. Probability x less than 3. So this is where we have to be careful because our calculators can only do less than or equal to. So if I want to be specifically less than 3, that means I'm looking at the probability of being less than or equal to 2. Because so remember, binomial distributions don't typically have decimal answers. And again, we're using, so we can't get a 2.5 or a 2.6, so decimals don't matter. So when we do 5, 0.4, 2, which gives us 0.68256. Okay. If we want to be greater than or equal to 4, we do 1 minus the probability that we're less than or equal to 3. So 1 minus binomial CDF, then it's going to be 5, 0.4, 3. Which is 0.91296. And then the probability x is greater than 4 basically just means the probability that x equals 5, because we only have 5 trials. We can also look at it as 1 minus the probability x is less than or equal to 4. Because we're looking at strictly greater than 4, we would do less than or equal to 4. I'm going to go ahead and use Binomial Pdf because we can do exact. So 5, 0.4, 5. Which is 0.01024. Even if you did 1 minus binomial CDF with 5.4 and then 4, you would get the exact same answer. So both of them end up working. We can also find mean and standard deviations for a binomial random variable. So just like we could do it for discrete, we can also do it for binomials. So because they have numeric answers, they have a mean and a standard deviation. The formulas are a lot nicer than the formulas we've been doing. So the mean for a binomial distribution is just n times p, so number of trials times the probability. The standard deviation is the square root of np times 1 minus p. So let's go ahead using Calvin's quiz, find the expected value and the standard deviation. So remember, expected value is the same thing as mean. So our expected value, our 5-question quiz, so n was 5, times the probability of success, 0.5, is 2.5. So we also want to interpret this in the context of the problem, just like we did with probability distribution. So if Calvin took many of these quizzes, we would expect him to get 2.5 questions correct. Which makes sense, because if we think of the fact that he has a 50% chance of getting each question correct, he should on average get a 50%. Okay. Next, we're going to look at the standard deviation. So the square root of n5 times p, 0.5, times 1 minus p, so 1 minus 0.5. That's basically 5 times 0.5 times 0.5, which is not 3, 1.12. So the typical deviation from the expected value is 1.12 questions correct. And that's not the only way we can word the standard deviation. Like, we could say that the number of questions correct varies by 1.12. There's a couple different ways you could say that. So looking at a new example now, suppose that the probability that any random freshman girl will agree to go with Nick to the senior prom is 0.1. Suppose Nick asks 20 random freshman girls to the prom. What is the probability that exactly one will say yes, that at least one will say yes? On average, how many freshman girls will agree to go with Nick to the prom? What is the standard deviation of this binomial distribution? So the first thing we have to do is make sure it actually is a binomial distribution. So first, are there two outcomes? Yes. The girls either going to say yes or no. Secondly, are there a fixed number of trials? Yes. He's asking 20. Are the events independent? Yep. Probability one girl says yes doesn't change the probability of the another one will. And is the probability of each trial the same? Yes. Each time the probability is 0.1. So in this case, X is going to equal the number of girls who say yes. So let's start with the first part, the probability that X equals 1. So this time we're going to use Binomial Pdf because it's an exact. And we're going to do the number of trials, 20, probability, 0.1, comma, probability of success, 1, which is going to give us 0.2702. Probability X is greater than or equal to 1. This is one of those cases where doing the formula by hand would not be fun, because you would have to do X equals 1 plus 2 plus 3 plus 4. So it's a very time-consuming process. So remember, this is the same thing as as 1 minus the probability that X equals 0. Because the only way you can be less than 1 here is if you are 0. So we're going to do 1 minus, and we're going to do binomial Pdf, and we are going to do 20.1 and then 0. So we get 0.8784. So pretty good chance at least one of them says yes. Okay. Next, we're going to find the expected value. So that's n, 20 times 0.1, which is 2. So that tells us that the average number of girls that say yes will be 2. And then the standard deviation. So the square root of n times p times 1 minus p. So it's the square root of 20 times 0.1 times 0.9, which gives us 1.34. So we can say number who say yes varies by 1.34 girls. The next thing we have to discuss is the geometric distribution. So a binomial variable had X equals the number of successes. A geometric random variable has a number of trials until you get the first success. So, for example, flipping a coin until you get heads, rolling a die until you get 6, throwing darts at a dartboard until you hit the bullseye. When we were looking at Calvin, one of the problems, on the very front page, we were talking about whether or not something was a binomial distribution, and we had drawing a card until you get a heart. It wasn't binomial. That's an example of geometric. So just like the geometric distribution, a binomial distribution has to have some properties. So it also must be binary. So each trial has to have only 2 possible outcomes, depending on what that is, success or failure. It must also be independent. And then the next is the trials until first success. Okay, so this time instead of n, a number of trials, it's a trials until the first success. And then lastly, the probability success has to remain the same. So there's not usually, you don't usually have to check that something is a binomial distribution because it's pretty obvious, because it'll just say, like, you know, here's the probability of something happening. How long will it take for the first one to be the 7th person? So it's not something that you have to check like a like a binomial distribution. So when we're talking about the formula, so we're going to use an example where you roll a 6-sided dice. Y is the number of trials until you roll a 6. So the probability you roll a 6 on the first trial is pretty straightforward. 1 out of 6. Okay? But what's the probability that you roll another number on the first trial, but a 6 on the second trial? Well, any other number, there are 5 of them. So 5 out of 6 times 1 out of 6, which is 5 out of 36. Probability that you roll another number on the first 2 trials, but a 6 on the third trial. So that's 5 out of 6 times 5 out of 6 times 1 out of 6. So that's 25 over 216. So we can also represent this in a distribution table where we have y and the probability of y. So first roll, second roll, third roll, fourth roll, continues. There would be, it can keep going forever though. There's no end. So 1 out of 6, this would be 5 out of 36, 25 over 216. This is 125 over 1296. And it keeps going. Probabilities just keep getting smaller and smaller. So, couple things. Can y be 0? No. Because we're looking at the probability of success, you need at least 1 trial. The smallest y can be is 1. When do we stop the table? We can't. Technically, you could go on forever without a success. So unlike probability distributions we were doing before, or even the geometric, there is an end. But for the geometric, there isn't. And then when it comes to the pattern, so if we're looking at probability of success, it's 1 minus p times p. So 1 minus p here is the number of failures. So if we look at B, 5 out of 6 are not a 6 times the probability of success, 1 out of 6. And that continues. Sorry, I put the number of failures in the wrong place. That should be an exponent. So if I had 2 failures, it'd be 5 6 squared times 1 6. So the probability of success can only happen once, but the probability of failure can happen multiple times, which then leads us into the actual formula. So if you have a probability of success P, K represents the trial that you get your first success. So the probability of y equals k, 1 minus p to the k minus 1 times p. So we have the probability of failure raised to the number of failures. And then we have a single success. So thinking back to our rolling dice, what's the probability that it takes you 5 rolls until you get a 6? So that's the probability that y equals 5. So we're going to do 5/6 to the 4th times 1/6. Which is 0.0804. What is the probability it takes you 10 rolls until you get a 6? So that's the probability y equals 10. So that's going to be 5/6 to the 9th times 1/6. Which is 0.0323. And then what is the probability that your 6 happens within 3 rolls? So this is the probability y is less than or equal to 3, which again, so this would be the probability y equals 1 plus the probability y equals 2 plus the probability y equals 3, which again, we could do by hand, but we can also use the summation formula on our calculator. So this time we would start at 1 and go to 3, and we would have 5/6 to the 3 minus x times 1/6 to the x. So remember, we go to math, then we go to 0. So x equals 1, 3. So 5/6 to the 3 minus x times 1/6 to the x. And we get sorry, I messed up the formula. So it should just be times 1/6 because it's always going to be 1 probability of success. Like, that's always going to be 1. So we get 0.4213. Okay. So the probability it takes at least 4 rolls to get a 6. So the probability y greater than or equal to 4. So when we did the binomial distribution, because we had a fixed number of trials, we could do greater than or equal to 4 because we had an end. But with geometric, we don't have an end. So we do 1 minus the probability that it's y less than or equal to 3. So 1 minus, we'll do our summation where x equals 1 to 3, 5/6 to the 3 minus x times 1/6. And because we just found that, 1 minus 0.4213, it's 0.5787. So geometric probabilities also have a calculator function. So if you want, so that's Geomet PDF. So remember, you do second bars And then E is geometric PDF, so that's if you're doing y equals something. And then geomet CDF is if you want to do less than or equal. So mean and standard deviation. Also, they have numeric outputs, which means we can calculate a mean and a standard deviation. So expected value is how many trials we expect before we get our first success. So we do 1 over the probability of success. Standard deviation, typical number of trials that deviate from the mean, is the square root of 1 minus p all over p. So for example, we have to start her old lawnmower, Iris has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. Find the probability that it takes her exactly 3 pulls to start the mower. So probability y equals 3. So doesn't start is 0.8, and then it takes her 2 tries times 0.2. I won't typically use the calculator way to find an exact value because it's not that bad of a formula. So 0.128. Probability it takes her more than 10 pulls. So that's the probability y is greater than 10. So we're going to do the probability. So I'm going to use the calculator for this. So that's 1 minus the probability that y is less than or equal to 9. And I'm going to go ahead and use the geomet CDF. So that's F when you go to second bars. And then you do the probability of success, 0.2, comma, your n, so 0.2, comma 9. And we get 0.8658. I forgot the 1 minus. Point 1342. Lastly, how many pulls do you expect it will take Iris to make? So this is our expected value. So 1 over p, which is 0.2, which is 5. So on average, you will expect Iris to have to pull it 5 times before the lawnmower will start. So the last thing we want to do is go ahead and summarize everything that we've talked about comparing binomial and geometric. So there's a lot of information in this section. So binomial random variables. So they have the acronym BINS. So binary outcomes, independent trials, independent probabilities. No, independent trials, I was right. Fixed trials, well, fixed number of trials, I should say. And fixed probability of success. Okay. Geometric random variables have the acronym BITS, so they're also binary outcomes and independent trials. But T is the trials until first success. and they also have a fixed probability of success. So the only real difference is the n and the t, whether or not we're looking at a fixed number of trials or a number of trials until our first success. So with binomial distributions, x equals the number of successes in n trials. Okay. Our formula is n choose k times p to the k times 1 minus p to the n minus k. Or we can use Binomial Pdf npk. If we're looking at x less than or equal to k, we could do each event independently, but I prefer the summation. So you start with x equals 0 all the way up to k. We do n choose k times p to the k times 1 minus p to the n minus k. And you actually plug in n. Or Binomial Pdf, well, you plug in p as well, which is npk. Probability for the mean, which we also call the expected value, is n times p, and the standard deviation is the square root of np times 1 minus p. You can do a table for a binomial probability distribution where you have the probability of the first, the probability of the second, probability. It's very similar to a regular probability distribution table. There's no real difference there. Then we have the geometric random variable, which is the number of trials until first success. Okay. So our formula is 1 minus p to the k minus 1 times p. You can use Geomet Pdf with p comma k, but I don't typically, because the formula isn't really that bad, so I don't normally use the calculator for that. If we're doing y less than or equal to k, I will use the summation. So we start with 1 and we go to k, and then it's 1 minus p and then you would do k minus x times p. Well, k is always 1. Or you can use Geomet CDF with pk as well. So mean, so expected value of y is 1 over p. Standard deviation is the square root of 1 minus p all over p. When it comes to the table, we don't really do one here since there's no end to the table. It would just be probability 1, probability 2, probability 3, probability 4, and you would just keep going. Okay. Please let me know if you have any questions over geometric or binomial distributions. There's a lot of information in these notes, so please let me know if you have questions.